Okay, so today I'm talking about uh, simplexes. Simplexes are just like collections of points, right, where every point is connected to every other point. All of them. Yeah, probably. Anyway. Okay, I'm going to start by drawing the nullitope. Okay, now I could draw more, but let's start with just one for now. Okay, with the nullitope, we have one object, which has 0 vertices, 0 edges, 0 faces, 0 cells, and 0 hypercells. To get the next simplex, a point, we will attach one vertex to all existing points. This point is a 0-dimensional object. We have one of them, and the number of vertices will be equal to the number of vertices that the nullitope had plus how many objects there are, since we're attaching one vertex per object. We still have 0 edges, 0 faces, 0 cells, and 0 hypercells. Continuing to the next simplex, a line segment. We attach another vertex, joining it with an edge. The line segment is a one-dimensional object. We have one object so far, and since we have one vertex from the point, and we're attaching one vertex for every object, which we have one object, we have 1 plus 1 equals 2 vertices. Now, the point had 0 edges, and we will now have one edge for every vertex, so 1 plus 0 equals 1. The line segment has 0 faces, 0 cells, and 0 hypercells. Moving on from the line segment, the next simplex we will look at is the triangle. The triangle is a 2-dimensional object. We still just have the one object. We have 2 vertices from before, and we're attaching one vertex for every object. We just have the one. 1 plus 2 equals 3 vertices. So this will now have a third vertex. The triangle starts out with one edge from the line segment, and it gets 2 additional line segments for each of the vertices of the line segment. So each of these join with the new vertex to form line segments. And now the triangle has 0 faces from the line segment, and it gets one additional face for each edge of the line segment, and that fills in this region here, forming a face. Moving on from the triangle, we get the next simplex, which is a tetrahedron, seen here in modular origami. Although, in a certain sense, this bit of modular origami is the true tetrahedron, but that's a story for another time. The tetrahedron is a 3-dimensional object. We still just have one object. We are attaching from the 3 vertices we had in the triangle, we're attaching one new edge for each object. 1 plus 3 is 4. And we have 3 edges from the triangle, and to that we'll be adding one edge for every vertex of the triangle. So 1, 2, and 3. 3 plus 3 equals 6. And for every edge, for which there are 3, we will be adding 3 additional faces. 3 plus 1 equals 4. And now, for each face that we had, we'll now have 1 cell and 0 hypercells. After the tetrahedron, we get the 5-cell. The 5-cell is a 4-dimensional object. We still just have the one object. We have 4 vertices, and attaching one vertex for every object, 1 plus 4 is equal to 5. So we will have 5 vertices. From the tetrahedron, we have 6 edges, and for each vertex, we'll have another edge, because we'll need to have them join with the new vertex. So 4 plus 6 is equal to 10. The tetrahedron had 4 faces, 1, 2, 3, and 4, and the 5-cell will then have an additional face for every edge of the tetrahedron. 6 plus 4 is equal to 10. The tetrahedron had 1 cell, as seen in here, and the 5-cell will have an additional cell for every face of the tetrahedron. 4 plus 1 is equal to 5. Finally, for every cell of the tetrahedron, the 5-cell will get 1 hypercell. And you might recognize these numbers from Pascal's triangle.